So everything is all right with the screen, or?
Yeah, perfect.
Super. So my name is Ewoud. I'm from the University at Leuven, indeed, in Belgium. I work at the NMR core. Today my presentation indeed is called long-term generation of longitudinal spin order controlled by the ligation of ammonia that enables rapid SABRE to the hyperpolarized NMR. So first of all, one of the most important requirements for doing hyperpolarization via parahydrogen using SABRE is using transition metal complexation chemistry, in which ligands, in this case hydrides derived from the singlet state of parahydrogen, and other substrates ligate to a transition metal, mainly a d-valence orbital block transition metal. So in recent years, this complex over here, the iridium cyclooctadiene IMS precursor, has become rather famous for its good abilities to transfer polarization, and when activated, it transforms into an 18-electron octahedral complex looking like this, in which the hydrides can transfer their spin order under the right conditions, low field conditions, and to these substrate molecules, mainly the equatorial bound ones. Now, ammonia, in this context of regular complexation chemistry, ammonia is a fairly good ligand. It's small, so it has a small Boltzmann angle, and in most of these cases, it also has fast ligation kinetics. But one of the most important aspects of ammonia in terms of SABRE is the fact that it has exchangeable protons. So the most important application that most of you know in terms of SABRE and ammonia is the fact that it can produce SABRE relay effects in, very importantly, aprotic conditions. So indeed here at low fields in strong coupling regime, the singlet state of parahydrogen transfers its spin order to the ligands, in this case ammonia, in which the protons of ammonia are hyperpolarized, and due to the fact due to chemical exchange or proton exchange, functional groups of other substrates not directly binding to the catalysts here are also being able to being hyperpolarized. So in this case, alcohols or saccharides can be hyperpolarized, drastically extending the substrate scope, which is a huge deal, of course. Now, this presentation here will be about the use of ammonia, not in case of SABRE relay, but in fact that it's just a great actually ligand which produces some awesome results I will show you next. So in our case, we actually used not ammonia itself, but an ammonium precursor, so the ammonium plus derivative, which in protic conditions with us, so in deuterated methanol, produces automatically, because of acid-base equilibria, produces ammonia. Now the trick is that this production of ammonia is perfectly pH controllable, so it's an acid-base reaction. So if we use different ammonium buffers, ammonium chloride, ammonium carbonate, which induces with deuterated methanol different pH values, we can control the ligation, or we control the production of ammonia in a SABRE system. So combined with iridium cyclooctadiene IMS precursor, we actually found a way to rationally design our catalysts in a way, and this is a sneak preview of what I'm going to tell. First of all, to extend polarization transfer routes to elucidation at high fields due to the controlled hydride asymmetry we can induce and the singlet triplet mixing here. Then also experimentally, we found an extension of hyperpolarization lifetime on the hydrides itself, even up to several minutes, in which is very handy for just a single activation, and you can elucidate the whole catalyst ensemble. And then the final thing is actually that ammonia itself simplifies the spin system, which has some awesome features that will be showed later. Now, first of all, the first step, so the experimental setup. First of all, a very important note: when you produce ammonia using these ammonium buffers in a deuterated methanol solvent, you immediately have proton deuterium exchange on all the exchangeable stuff, which made that the main ligand that we're actually binding to the catalyst is deuterated ammonia. So in this case, a normal deuterated methanol system with iridium precursor was combined with ammonium chloride and a little bit of pyridine, ammonium carbonate and a little bit of pyridine, and ammonium hydroxide solely. Now, what did this do? It actually provided us control over how many pyridine ligands, or how many deuterium ammonium ligands are actually ligating, in which we could create these four complexes here, which have a decreasing number of pyridine and an increasing number of, in this case, deuterated ammonia. Now, all of these catalysts could be analyzed of their low field SABRE behavior and also effects on high field, which is the following topic. So first, at low field, these complexes show indeed mainly on pyridine then coherent polarization transfer from parahydrogen to pyridine in this case. Now at high field, what happens, because we can induce this hydride asymmetry in a controlled way, and singlet triplet mixing, so that is already the topic of many of these talks today. So what happens, the singlet state, when the parahydrogen is connecting to the catalyst over here, which is asymmetric, the singlet state evolves under the chemical shift difference of these two hydrides. Now, one of these terms of the singlet state in the beginning is the two-spin order here, the longitudinal magnetization, which is invariant under this chemical shift difference, while the other spin states, which is a zero quantum coherence, actually just dephase and get lost. So the only term at high field from these hydrides that is remaining is this longitudinal two-spin order. Now, this sort of bad way of thinking is based on the beautiful research of Marco Tessari, where he uses other ligands. In this case, he uses a triazole, but in our case, we use this deuterated ammonia, which has some beneficial effects. So experiment-wise, so the first thing we noticed, obviously, of doing all these different ammonium buffers together with the pyridine system, is indeed a difference in hydride region, which is expected from the catalyst structures we are going to make actually. In this case, they are antiphase when the hydrides are asymmetric, which is obviously from the singlet triple conversion happening at high fields, because the longitudinal two-spin order pulse by a power pulse will give antiphase magnetization in both hydrides. As they are varying, they are also we can actually, by later experiments to the high field experiments, we can characterize all of these hydride peaks. Now, one of the most important feature actually in this case is we also investigated the lifetime of this hydride magnetization with a field cycling device in which at low field, so this low field setup here, in which at low field we activate the catalyst with different ammonium buffers, and we send it to high field where singlet triplet mixing is activated. Because of there, the chemical shift difference is much higher because of the large Zeeman field, and we introduced a variable A and then checked how many magnetization is left after a 45-degree pulse. Now, these were the results for a standard pyridine system. As expected, it's not a singlet triplet mixing here, it's just magnetization being produced at low field from hydrides, which has a very fast decay. With ammonium chloride, everything began to be on longer, and then with ammonium carbonate, we got actually hydride magnetization, which existed in a T star over 30 seconds, in which we could use this magnetization just in order of minutes to check which catalyst structures we actually made. So therefore, after a single activation, this activation has also been done at low fields. You can even do it also at high fields. But after a single activation, we just could run a fast 2D obfuscose experiment with some dust sampling in there, 2.5 minutes, and we got this really resolved obfuscose plots in which we could elucidate all the catalysts, even the long-range couplings, so the coupling between the pyridine octoproton of the pyridine and the trans hydrides were easily elucidated using this fast technique and using this sort of experimentally observed lifetime the deuterated ammonia induces on these hydrides. Now, the final step we investigated is low field behavior. So the low field behavior mainly on the pyridine hyperpolarization, because all the catalysts are decreasing in pyridine numbers, and we did some field sweep experiments in which we, again with the field cycling device, activated the catalyst at low field, and varying the field, we checked for the polarization efficiency at high field, which is plotted here. Obviously, this field sweep curve is already being performed multiple times, which has this typical way of it's looking like here, you have one layer anti-crossing at around 6.5 millitesla, which is the maximum polarization. Now, what did we see? If we added ammonium chloride, everything became a little bit sharper in resonance conditions, but the main thing here is actually if we use ammonium carbonate and our main species is looking like this, deuterated ammonia, and only one pyridine ligand, our system became so simplified with the deuterated ammonia being not very interacting because of the deuteration with the spin system, that for the first time in a simple 4-spin system, in this case also with pyridine, some similarities finally could be seen experimentally in the way the simulations on these field cycling experiments actually that were simulated already a long time ago, were always in a simple 4-spin system with on the Zochronos hydrides here, we're actually always seeing two layer anti-crossing positions. And here, finally, in a simplified spin system with the fact that it's deuterated ammonia, we could finally see these multiple behaviors. And even in some further simulations, but these were performed by Leuven and I think Stefan Knecht, they were with the continuous repolarization with parahydrogen. They also saw some oscillations. These were, I think, simulations only performed at low field conditions, also measuring at low field the polarization, but still they have some oscillations going on. And I think even in this data, you can see this oscillation actually also going up and down, even at higher fields. So with this, I want to conclude, and with the fact that you can use deuterated ammonia for rationally controlling the ligation of your catalysts, which induces, in this case, an extension of polarization transfer routes because of the hydride asymmetry and the singlet triplet mixing for generation of this longitudinal magnetization, which is accompanied by the extended lifetime. Also, we experimentally observe it, still are figuring out, okay, what is the real reason for this long lifetime. And also it simplifies the spin system in which this awesome unification between theoretical and experimental field sweep experiments are being seen. Now, one of the major future prospects is actually that, as I said in the beginning, deuterated ammonia is a very small ligand with a very small tolerance angle in which it doesn't take much place on the catalyst, whereas we think that more bulkier than more important substrates than pyridine in this case can also be attached to the catalysts, and with all these nice features here, we can extrapolate all these nice features towards elucidation of catalyst structures and hyperpolarization at low field, at high field of more important bulkier substrates. This was the end of the presentation. I want to thank all these people for letting me do this awesome research, and in particular Professor Francis Taulel, which I discussed many of these topics with. He also passed away a few months ago. So I thank you for your attention, and I open to any questions.
Thank you so much, Ewoud. Amazing talk. Yeah, nice to see how you're able to control the polarization using ammonia. Very nice talk. Okay, so there's a question here. So it says from an anonymous attendee, it says, can changing the pH, if you change the pH, do you see any protonation of pyridine nitrogen, which could affect its binding or exchange rate?
I think you have to repeat the question. So what
if you are changing the pH,
yes?
Do you ever see protonation of the pyridine nitrogen, which could affect its binding or exchange rate?
No, so changing the pHs here with the different buffers, and we don't see the proton deuterium exchange on the pyridine because we are in such an exchangeable system with the deuterated solvent, with the deuterated ammonia, deuterated methanol, sorry, that this connection between pyridine having an H or an D, we cannot see it. So no, we don't see any influence.
Thank you so much.